Okay. Good morning, viewers. Welcome to the class of Analog and Digital Electronics, the series of lectures. So we have been started with the formation of the PN junction diode, and then we have studied the working principle, operation, and the characteristics of the PN junction diode, followed by some of its application as a switch. And we have seen some of the behaviors of the PN junction diode in the form of diode resistances and diode capacitances. And after this, we have also introduced the special diodes, starting with the avalanche diode, Zener diode, tunnel diode. And in the recent class, we have studied the photodiode and a light emitting diode. And now, after this, we will introduce what are the major applications of the PN junction diode. So, where we apply this, what is the use of PN junction diode to the engineers? So, the answer is, one is switch, as we have already seen, and now we are going to see about the rectifier operation. So, the today's class outline is what is a rectifier, what are the different types of rectifiers, and we will study in detail one of the rectifiers, that is the half wave rectifier. And whenever we study a rectifier is accompanied with a filter. So we have to study rectifier and rectifier with a filter. So first definition of the process of rectification. So rectification is the process of conversion of the alternating current into the direct current. So what is AC DC? I'll show in the next slide with a graphical view. So a rectifier is an electronic device that converts AC voltage or current into DC voltage or current. So a rectifier, it converts alternating current into the direct current. So mostly it is used to convert the supply voltage or the mains voltage into the DC voltage in the power supply section. Because in the household, what we get the supply is the alternating current. It is coming with a voltage of 230 volts and 50 hertz frequency. And all our electronic gadgets that we use in our daily life do not require that much of voltage. 230 volts of voltage is not required. Mostly they operate with lower voltages around 5 volts, or at the maximum they can go to a 15 volts. And the main supply is of AC nature. AC means with respect to the time they will vary periodically. So the input supply that we get is in the form of a sine waves. But what we require to run our electronic devices is the DC. DC means a constant supply we need. That is the difference between the AC waveform and DC waveform. So here you can find two waveforms. This is the AC waveform. This is the AC waveform and this is the DC waveform. On the positive x-axis, time is taken in this graph, and on the positive y-axis, magnitude of the voltage or current is taken. So current or voltage varies with respect to the time. When it varies with respect to the time, that is called as the alternating or changing with respect to the time. And coming to the other graph, on x-axis, positive x-axis, time is taken, and on the positive y-axis, magnitude is taken. That is, if it is voltage, it is measured in the volts. If it is current, it is measured in the amperes or milliamperes. And you can observe the graph. This is exactly parallel to the x-axis. That means it is maintaining a constant voltage throughout its operation. And such type of supply is called as the direct current supply or the DC supply, which is required by any of the electronic gadgets that we use in our daily life. So there is a requirement to convert from the AC to the DC. So there is a requirement to convert from the AC to the DC. So what is the circuitry involved in the conversion of the AC to the DC. That is given in our next slide. So this is the complete block diagram of the process of converting a AC supply into the DC supply. So first one is the transformer. First circuit is the transformer. Second is the rectifier circuit. So it is naturally called as a diode rectifier. A rectifier means obviously it is made up of a diode. So it is called here as the diode rectifier. Followed by the next block filter. Followed by the next block regulator, that is voltage regulator. And ultimately we are supplying this to a load terminal. So what it is doing? First we'll talk about the transformer. So what is the necessity of a transformer? The transformer is used here is a step down transformer. You might have already studied these basics in your previous year in the subject called basic electrical engineering. I am once again revising. So input supply, I said the supply voltage coming is 230 volts with 50 hertz. But in the diagram, it is given as 120 volts, 60 hertz. You should get a doubt. So 120 volts, 60 hertz is the supply of the American country. India and its nearing countries will use the supply of 230 volts and 50 hertz frequency. And the waveform is like this. This is a single wave is given. This is one complete wave. Okay, remember this. Now what the transformer will do is, it will convert this 230 volts 50 hertz supply into the diode withstanding voltage, that is nearly to the 12 volts or to the 15 volts. And what the rectifier circuit will do is, this supply is bidirectional. That means one positive variations are there and negative variations are there. This will be converted into unidirectional, that is in the form of unidirectional current. This is called as the pulsating DC. So what rectifier will do? Rectifier alone will not convert AC to DC. Rectifier will convert the AC into pulsating DC initially. And you can compare this waveform with the DC waveform that we have seen in the previous slide. This is not a DC. So in the process of converting DC, in the process of converting AC into DC, first circuit is rectifier, followed by a filter. So these are the AC content again in the output of the rectifier. To filter this AC content, we are using a filter. So what filter will do? Filter will do the unwanted, will remove the unwanted components. Here, these are our unwanted components, variations. And these variations are somewhat reduced in the output of the filter. So this is, here you can see. Now, even this is not a perfect DC. It is having some changes in that. The supply is changing with respect to time again. And this unregulated supply is regulated or made constant with the help of a voltage regulator. So the final output obtained is this, that is exactly parallel to the x-axis. And we have already seen voltage regulator. So what is voltage regulator? A GINA diode can be used as a voltage regulator, which will maintain a constant voltage across it when it is reverse biased. This topic we have already studied when we completed the GINA diode. You can relate this now. So this is the block diagram of total conversion of the AC into the DC. Now what are we studying is, we are studying the rectifier and filter in this class. Regulators we have already studied. Now we'll go to the next section. So here rectifiers are classified into 3 categories. So what is the basis for the conversion? The basis for the conversion of the rectifiers is for how much period the rectifier will conduct. That is for a half period or for a full period. So basically the rectifiers are classified into half wave rectifier and another is the full wave rectifier. Bridge rectifier is also a full wave rectifier, and the difference between the full wave rectifier here and the full wave rectifier here is, here we are using 4 diodes in the form of bridge, and here we are using 2 diodes connected in parallel combination, and here we use a another special category of transformer that is called as the center tapped transformer. When we study the full wave rectifiers, we'll see in detail about that. So as of now, what you remember is these two are full wave rectifiers. That means they will convert the full sine wave into the DC. And what half wave rectifier will do? It will convert only half of the sine wave into the DC. We'll see that in detail in our next slide. So what is a half wave rectifier? A type of rectifier that converts only the half cycle of the alternating current into the direct current is known as the half wave rectifier. So as just now I have said, it will convert only half of the wave. It will not convert the full wave. A half wave rectifier that converts only the positive half cycle and blocks the negative half cycle. How it does, we'll see with the circuit diagram. So this is the full paged circuit diagram of a half wave rectifier. You can find the AC waveform that we are giving. This is a AC waveform which is consisting of 2 cycles. Starting from origin to 2x is 1 cycle, and same shape or same pattern is repeating. So this is the second cycle. So in this waveform we have seen 2 cycles. From 0 to 2x is 1 full cycle, and 0 to x is the half cycle, and from x to 2x is the remaining half cycle, so that it makes a complete cycle. And what is shown here, this is the voltage. And maximum voltage is reached at this point, positive maximum, and it is the negative maximum of the waveform. Now, the output of the transformer is connected to the PN junction diode such that the diode gets forward biased, and the diode is connected in series with it a resistor, that is a load resistor RL, and some current is made to flow through the load resistor. Because of the current flow through the load resistor, I into RL product will be the output voltage V naught or VL, load voltage we can treat. Now how the circuit is operating, let us study this. Now during the first half cycle, so what I mean by this, during the first half cycle, I divide the operation into 2 half cycles, first half cycle and second half cycle. So here you can see from 0 to x is the first half cycle. So during the first half cycle, 0 to x, the supply is positive. The supply is positive. That means positive terminal is connected to the P side. Of course, the negative terminal is connected to the N side. So during the positive half cycle, the diode D will be getting forward biased. So when the diode gets forward biased, it will act like a on switch. It allows the current to pass through it. And the current that is flowing through it is I. The same current will flow through the load resistor RL, so that some voltage will be dropped across the load resistor RL, and that is plotted in the output like this. During the 0 to x, whatever the input supplied, that will be appearing across the output in the form of this. Next, during the negative half cycle, from x to 2x, what is the supply? The supply is negative. That means negative terminal of the battery is connected to the P side of the diode, and positive terminal connected to the N side of the diode, so that the diode is getting reverse biased. When the diode is reverse biased, the diode will be acting like a off switch. That means its resistance will be very high and it will not allow any current to pass through it. Hence, the net current that is flowing in the circuit is 0. That is, I is 0. And voltage drop is also 0. Because current is 0, I into RL also will be 0. So that from x to 2x, it is 0. Again, from 2x to 3x, same, it is second cycle. So from 2x to 3x, the output will be there. From 3x to 4x, there won't be any output. So is this clear? That is, during the positive half cycle, I am repeating, the diode will be forward biased and it acts like a on switch. Due to this, current will flow in the load and there will be a output voltage drop. And during the negative half cycle, the diode will get reverse biased and current will flow into the load and there won't be any supply. And the dotted line is the VDC or V average. About this we will talk in our next slides. So this is whatever I talked just now, it is mentioned in the slide. So here some of the parameters, qualitative parameters that are to be measured for a output of a rectifier. One is the VRMS, stands for root mean square value, and another is the VDC or V average of the output of the rectifier. So VRMS is derived to be V peak or V maximum by 2, and VDC is V peak by pi. This I will derive in the on the board when I take the live class, right? So where VDC, V average DC, and V peak is the peak value of the voltage or maximum value of the voltage. RMS is the root mean square value. So some of the characteristics, some more characteristics of the half wave rectifier or full wave rectifier will be the same. One is the peak inverse voltage. So what is peak inverse voltage? The peak inverse voltage is during the reverse biased condition, the diode has to withstand because of its maximum voltage. So there will not be any current flowing through the diode during the negative half cycle. During that time, what is the voltage available across the diode? That is called as the peak inverse voltage, and that is equal to Vm for the half wave rectifier. So this derivation, I will do it in the class. Don't worry about this. I will derive it on the board. I cannot explain with the PPTs. And regulation is percentage regulation. It is the difference between the no load voltage. So without applying the load resistance RL, we measure the voltage across that when we do the practical, and we apply the load and we'll measure the voltage, that is called as the full load voltage, V full load. And regulation is V no load minus V full load. Percentage regulation is V no load minus V full load by V full load into 100. It is a numerical quantity that we'll derive it in the class, and we'll do it practically in the laboratory also. So efficiency is 40.6 for the half wave rectifier. This I'll derive in the class. It is the always in any circuit, efficiency is always ratio of output to the input. So here output is the DC power and input is the AC power. So PDC by PAC is the efficiency. And the ripple factor, one of the very important parameter. So it is defined as the amount of AC content present in the output DC. So what the ripple factor will signify is the rectified output is not purely DC. We already seen in the waveform that it is also consisting of some pulses. So it is consisting of some AC. So it will measure the AC content of the rectified output. So this is for half wave rectifier 1.21. So if it is more means the rectifier is not done its job. If it is lower value means the rectifier has done its job a better way. So for half wave rectifier it is 1.21 and for full wave rectifier it is 0.48. I will derive it in the class, don't worry about this. And one more is the transformer utilization factor. This also I will derive. And now we will see the advantages of a half wave rectifier. So first, it is very cheap, very simple to construct because we are using only single diode, and very easy to use and less number of components. And drawbacks or disadvantages are ripples are more. When we study the full wave rectifier, we will come to a conclusion that half wave rectifier has the more ripples. Ripple content is more, that is ripple factor is high, and a tuff is very low. Rectification efficiency is low, and it generates the harmonics, as these all we have seen in the output of the half wave rectifier. And just now we said that there are some ripples in the output of the rectifier. Then what is the next block in the block diagram of the conversion of AC to DC, followed by a filter? Then to remove those pulses or AC components from the rectified output, we will apply this output to a filter. So half wave rectifier with a capacitor filter, and the filter is realized by connecting a capacitor in parallel with the load resistance RL. So the output of the half wave rectifier has too many ripples, and it is not very practical to use this output as a DC source. To smooth this pulsating output, a capacitor is introduced across the resistor. So this capacitor will behave as a filter. And how it works, let us see with the diagram. So this is the half wave rectifier circuit with the capacitor filter. The same AC input is given, sinusoidal input, transformer, step down transformer, diode, load resistance RL, and what is extra component? This is a capacitor C is introduced, which is in parallel to the load resistance RL. So this is the circuit diagram of the rectifier, half wave rectifier with the capacitor filter. So how it works? So during the positive half cycle, the diode will be on, and current flows through the load resistance RL and also into the capacitor C. During this, the capacitor C will be charging. So we already know that the capacitor will charge initially and afterwards it will discharge. So during the positive half cycle, the capacitor will charge to its maximum. So this is the maximum value shown in the output. And when the negative supply, that is from 0 to x, x2 to x. During x2 to x, during the negative half cycle, the capacitor will start discharging. The capacitor will start discharging. That is, the capacitor will start discharges. Until how much time this will discharge? Until the next positive half cycle comes, it will start discharging. And now you should get a doubt that these two are not uniform. Why these two are not uniform? The process I said is ideal process. That means neglecting the cut-in voltage of 0.7 volts. Our diode will have an inbuilt cut-in voltage, that is the threshold voltage, that I have denoted in my explanation, throughout explanation. If we take the cut-in voltage into figure, then the current starts flowing through the diode after the cut-in voltage. That is why it is like this. And the next cycle also starts when the input supply starts at a cut-in voltage. That's why it has fallen up to this much time. And the same thing will repeat for the second cycle. So this is the output of the filter. That means rectifier with filter. And you can see very clearly input waveform to the rectifier, output of the rectifier, and output of the rectifier with filter. So that is the end of the class, and we will see in our next class about the full wave rectifiers. Thank you.